In this lesson, we're going to talk about approximating the sum of a convergent series. And the basic way to do that is to just stop after a while. So instead of going to infinity, you just stop after a certain number of terms. And because the series converges, you figured that you're getting pretty close to the correct answer. We're going to label the partial sum or the truncated sum S sub k. It's the sum from n equals 1 to k of the series. Now, of course, when you do that, you're approximating, and therefore there is an error. Now, the error itself is called R sub k. So it depends on how many terms you've taken. If you've taken 20 terms, it's R20. And essentially what it is, well, whatever the sum of whatever remaining terms is what the error is. So since you've gone from 1 to k, the error is the term starting at k plus 1 going all the way to infinity. So this is something that's useful to know, at least to if you can approximate or have an upper bound of what the error is, then you have a sense of how close you got to the correct answer. Obviously, if you know exactly how big the error is, well, then you actually know the sum. So you're always going to be approximating the error, not calculating the error. So here's the description of one way to approximate the error. So I've done this again in relation to an integral. So if this is the function f of x that's modeling the series so that the a(n) and the f of n match up, and if I have k here and k plus 1 here, it's k plus 2, etc. And if I took the y-coordinates here, that's the a sub k plus 1, that's the a sub k plus 2, that's the a sub k plus 3, and I drew rectangles to the right like that, then these rectangles will have an area that is larger than the area underneath the curve, or the integral. Now remember, these rectangles starting with the ak plus 1, those add up to what's called the error of rk. So you've truncated, you've added up all the rectangles until k, and then you're saying that's your approximation, and then the remaining rectangles are the error. Now, those rectangles have an area larger than the integral area starting at k plus 1. So what we say is the integral from k plus 1 to infinity of fx dx is going to be less than that error rk. However, if I did the exact same thing and I drew my function with the an equals f of n, and I start my k plus 1, that's my ak plus 1, ak plus 2. So again, these values represent, if you add them up, the error. But if I instead drew the rectangles to the left, well then these rectangles now have an area that is smaller than the integral. However, that integral, because I drew it to the left, started at the k coordinate, x equals k, because the ak plus 1 region was drawn to the left so that it bordered at the very end of the rectangle, the x equals k. So the area underneath these rectangles, which is the error, is less than the area underneath the curve or the integral starting at k. So r sub k is less than the integral from k to infinity of f of x dx. So if you put this together with this, what we can say is that the integral from k plus 1 to infinity is less than the error, and that error is then less than the integral from k to infinity. So we have a lower bound and an upper bound of our error if it is possible to create a function whose integral we can calculate starting at either k plus 1 or k, depending on whether we want a lower bound or an upper bound for our error. So here we're trying to determine the number of terms necessary to approximate this sum, n goes from 1 to infinity of 1 over n cubed, correct to 2 decimal places. Now, in order to be correct to 2 decimal places, that means when you go to that third decimal place, you should be rounding appropriately so that the second decimal place is still accurate. So in order for that to happen, you know that the error, rk, has to be less than 0.005, so that when we round, then that second decimal place is still accurate, or at least the approximation is within 0.01 of the correct answer because of our rounding situation. So now I'm going to write an integral statement that relates to the error. And what I can say is that I know that the error, RK, is less than the integral from k to infinity of, in this case, 1 over x cubed dx, because that's the function that maps this series. And then if I can let that integral be less than 0.005, then I've guaranteed that the error, which is less than that integral, is going to be less than 0.005. And then I will identify what k value makes that happen, and then I'll be all set. So let's go ahead and set up this integral. So the integral from k to infinity of 1 over x cubed dx is going to equal the limit as b goes to infinity of the integral from k to b, and I'm going to write x to the negative 3 dx, and then that's the limit, and then I take the antiderivative, the limit as b goes to infinity of negative 1/2 x to the negative 2 evaluated between k and b, which is going to be the limit as b goes to infinity. And I'm going to write that as negative 1 over 2b squared, and then minus negative, so plus 1 over 2k squared. And now that then, as b goes to infinity, this becomes 1 over infinity, so 0. So this whole limit is 1 over 2k squared. And I want the 1 over 2k squared to be less than 0.005, which is 1 over 200. Or that's 0.005. So what I'm now going to do is I'm going to take the reciprocal of both sides of this inequality. I know that in order for this fraction to be less than this fraction, then this denominator has to be bigger than this denominator, because after all, the numerators are the same. So really what I'm saying is that 2k squared has to be greater than 200. In other words, k squared has to be greater than 100, so k has to be greater than 10. Now k has to be strictly greater than 10 to guarantee this inequality, which then guarantees this inequality. So I'm going to say use k equals 11. So we've now discovered that if we go from 1 to 11, if we do that sum from 1 to 11, then that answer will be close enough to the actual sum that the first 2 decimal places are accurate. In other words, it's correct to 2 decimal places. So we can either state that as we need 11 terms, or we can say sigma n equals 1 to infinity of 1 over n cubed is approximately sigma n equals 1 to 11 of 1 over n cubed, correct to 2 decimal places. Now, if you actually wanted to calculate what this series was, you could add up 1 over 1 cubed, 1 over 2 cubed, etc. Or there are things on the calculator, there's buttons on the calculator that can do that series for you. So that would be another way to do it. But the question did not need that. It just wanted to know the number of terms necessary, and the answer is 11 terms are necessary.